Conference topic: Electric Sails for Interplanetary Exploration and Science. Electric sails, e-sails, are a promising propulsion technology that seek to enable high-characteristic propellantless acceleration for spacecraft to reach distant and/or difficult-to-reach orbits such as rapid transit to heliopause. The e-sail system exchanges momentum by using positively charged electrostatic tethers to repel solar wind photons to push it through space. This concept was first theorized by Pekka Johnhoon in 2004, with further developments occurring, including a NASA Innovative Advanced Concepts Phase 1 and Phase 2 hosted out of NASA's Marshall Space Flight Center, MSFC. These developments led to further maturation of the overall system, and this paper is designed to help identify different design sensitivities of an integrated electric sail system. To approach this, a small team at MSFC took an in-house developed 3 degrees of freedom 3DoF simulation tool and a trajectory modeling tool to look at different design parameters and to determine a potential ideal e-sail configuration. An e-sail system has different design architectures, including a barbell design, hub and spoke design, and a potential hybrid solution. The barbell design features 2 equally massed satellites that spin around a central point in the tether system. The hub and spoke design features a large central spacecraft with small end spacecraft to aid in formation control of the overall e-sail system, leveraging elements from both the hub and spoke and barbell design. A hybrid option exists where one could have a larger central mass and 1 or 2 tethers extended to a smaller end mass. In summary, the hub and spoke design is the ideal configuration for e-sail, with tethers spanning kilometers to achieve the design characteristic acceleration of at least 1 mm/s2, with this architecture being the focus of this study. Different key design parameters were varied as part of this study. These parameters include the total number of tethers, the length of the tethers, spin rate, relative spacecraft mass, tether voltage, inertia per tether, and impact of slew rate changes. These results started from an internal MSFC technology demonstration mission design, and then the parameters were varied with engineering judgment to ensure that the results were consistent with expected results. These were varied in the MSFC 3DoF tool and compared to baseline results to generate a candidate ideal e-sail design system. These results were then used to help inform the mission analysis design for the system. The 3DoF trajectory optimization was performed in the Astrodynamics and Space Science Enabling Toolbox, ASSET, and utilized collocation optimization of control vector pointing, with the objective function being transfer duration. A representative model of the e-sail force was derived as a function of the sun pointing vector direction. This model was initialized with a zero sun incidence angle, SIA trajectory for the initial guess generation, then with a portion of the mission-optimized SIA time history for fast outbound transfers. After the trajectory is hyperbolic relative to a heliocentric frame, the SIA is maintained at 0 degrees except for any needed trajectory correction maneuvers. This trajectory optimization looked at different characteristic acceleration values to analyze the impact it had on mission performance. As a result of this study, the team can best inform mission designers and technology development efforts to mature the e-sail system. This study will allow mission designers to have defined rules of thumb to design an e-sail system to meet desired mission needs, as well as providing several sample mission profiles. These design drivers will inform maturation efforts on which design requirements to consider for an integrated e-sail design. Conference topic: Mathematical modeling of space tethers, dynamics, controls. Over the past 2 decades, electric solar wind sails, e-sails, have emerged as a promising propulsion technology for space exploration missions. Utilizing the momentum of the solar wind, e-sails deploy a mesh of wires to generate electric fields, enabling propellantless propulsion. This technology offers significant advantages, including extended mission durations and potential applications in various space missions, such as small body exploration, multi-target exploration, and establishing artificial equilibrium points in space environments. Existing studies on trajectory optimization and guidance, some considering the uncertainty in the solar wind, indicate the need for adaptive operation throughout a mission. This involves varying the electric voltage at which the cables are modulated, requiring multiple on-off events for interplanetary missions, and executing maneuvers to modify the attitude of the E-sail and hence the orientation of the generated propulsive force. Furthermore, various publications have analyzed the dynamics of the E-sail, commonly considering steady-state operation characterized by constant and equal voltage for all the tethers, constant attitude only modified by rotation around the longitudinal axis of the sail with constant angular velocity, and constant cable position with respect to the body fixed coordinate system. However, there is currently a gap regarding the feasibility of achieving stable and progressive power above the E-sail to ensure its evolution to steady-state situation. This work introduces a method for computing the optimal control law to facilitate the transition of the E-sail between two steady states, corresponding to distinct voltage levels in the tethers. Leveraging principles of dynamics inversion applied to the E-sail model, this innovative controller enables adjustments in propulsive force to meet the demands of optimal trajectory planning and guidance algorithms. The architecture considered for the E-sail is that of a central vehicle and radial tether stabilized by the spin of the entire assembly and the presence of a remote unit at the outer end of the cables. The E-sail dynamics is considered through a modeling approach that treats it as a multi-body system, MBS. In contrast to this work considers a minimum set of local coordinates formulation that leads to an ordinary differential equations, ODE system. Selected coordinates include Euler angles to describe the attitude of the central spacecraft, angular rates expressed in body axes to depict the angular motion of the system, and angular magnitudes to establish the local orientation and position of the tethers. The calculation of the control law is posed as an optimal control problem, OCP, which is solved using the direct transcription method, resulting in a nonlinear programming, NLP problem. The cost function is established in terms of system coordinates and controls, allowing for bounded evolution of variables associated with internal dynamics while minimizing control requirements. The fourth-order Runge-Kutta integration scheme used constitutes the nonlinear equality constraints that the optimization problem solution must satisfy. Additionally, once the reference trajectory and open-loop optimal control are determined, the tracking problem is addressed through a receding horizon model predictive RHMPC approach. It is noteworthy that unlike proposals in other works, this study does not consider the application of control forces on remote units, too. This fact complicates the system dynamics control as it reduces the control variables. However, it is considered an advantage as it simplifies the complexity of remote units by not having to be equipped with small thrusters, reinforcing the propellantless nature of the E-sail. Studies' findings on a typical E-sail configuration illustrate that stable evolution between equilibrium states can be achieved by appropriately combining temporal evolution of control moments and electric voltage in the tethers. Furthermore, the use of an optimal control problem formulation is confirmed to be an efficient and flexible strategy for resolving the inversion problem of the proposed E-sail multi-body model, despite its non-minimum phase dynamics and substantial size. Finally, the applicability of RHMPC algorithms is proven for the system tracking during the transitioning.